for this session, we have Rupesh and Michelle, who are NASA Openscapes mentors. Rupesh is a research staff member at the Oak Ridge National Laboratory, working at the NASA DAAC. Rupesh has extensive background in remote sensing, like to vegetation images, measurements, and cyber infrastructure development, data science. And we also have Michelle, who has a background in ecology, geospatial science, and remote sensing to also support the NASA Oak Ridge National Laboratory. And also she leads data management strategies for the Dover NGEE Arctic Phase 4 team. And with this, we're going to have floor open for Rupesh for the presentation.
Thank you, Ronnie. Let me share my screen. Can you hear me all right?
Yeah, I can hear you.
Rupesh, could you please put a link to your slides in the chat?
Okay.
Yeah.
Before I do that. Sorry.
Okay.
Okay. Yeah. Can you access it? It's in the Google Doc. I think I shared for everyone.
Yes, I can see the slides. Thank you.
Okay. Can you see my screen as well, right?
I can see your screen.
Okay.
Yes, and I can see your slides. Perfect.
Okay, thank you. So before I start, I want to just tell, Michelle and I both have been involved with the OpenScape for quite a while, and we have learned so much from the OpenScapes community. So mainly in the area of like the field of technology, such as cloud-based access, and also I would like to thank Julie for her leadership and vision on bringing all the NASA DAACs together into this collaborative place that we can share our thoughts and learning freely. So thank you for that. And so today, as Ronnie said, we'll focus especially on the metadata needs for suborbital data publications with NASA Earth data. So we'll mainly talk about metadata. So that also means that we will go into some nitty-gritty and details. So all of which might not be necessarily needed, but as a data provider, so it would be good to know what goes into our system before a data is published at NASA Earth data. So with that in mind, before I go into details, I would like to quickly show some of the NASA Earth data pages. So this will give us an idea of how metadata is being used in various NASA interfaces. So this is an instrument page on the left here from the NASA Earth data website that lists all the NASA instruments which has collected and posted data to NASA Earth data. So there are almost like 200 instruments there now. So if you click on one of the instruments, it will show an instrument landing page. So here is an example of an UAV SAR instrument. So if we click on this data and tab tools over on the top here, so it will display all the listings of the UAV SAR datasets. So the data are also listed by the instruments. And then, so this is similar to the instrument page, but this is a platform page. So if you look into this air-based platform, the platform are organized by air, land, water, etc. And if we just look into the air-based platform, like shown in the middle here, so it will list different aircrafts that NASA has used to fly and collect data. So one of the aircraft is NASA ER2. So we just flown many instruments ranging from Avis to Master and to Prism, I think. So if you click on the data and tools tabs here as well, it will list the similar page with all the data that has been published that are collected with the same platform, this plane that NASA owns and operates. And there is another page in addition to instrument and platform that's called project pages. So on the left is the listing of all the projects. So projects are mostly the NASA campaigns, such as EV missions. So each project has a landing page, like shown here for the Atom. So Atom was a EV2 project. And then, so the new EV4 mission that most of you are part of would also have a similar project landing page when the data are ready to be published as well. And so the data set, again, will be listed in the similar way. So clicking on the data and tools here will list all the data that is available for that particular project. So this project, instrument, and platform kind of shows a nice connection between data sets and these projects, instruments, and platform. So this is all possible because the metadata that goes into publishing the data sets are all tied in behind the scene, and that makes it happen. So now we can go and talk about metadata. So let's look quickly into describing the metadata. So both in general terms and also in terms of how NASA Earth Data talks about metadata as well. So even if we all know what metadata means, so it might not all be same for everyone. So just to bring everyone into the same thinking, so metadata is usually described as a structured form, such as a JSON or XML. It used to be XML mostly, but now it's more JSON format. And it usually follows standards and schemas. So the main goal of metadata is to improve data discoverability. So both humans and now AI and machines can find it and also know what, when, how, where, and who of the data sets as well. So the first, so metadata is about the data itself. So the data is also called data collection in NASA's term. NASA Earth Data usually like to put similarly collected data files with the similar variables into one collection. So I have shown a jar full of cookies to represent one data set. So there are different kinds of cookies there might be sometimes, but there are usually similar cookies into one jar. And so jar is a data set. So a data collection usually has a unique identifier such as a DOI and a landing page and a version and also a citation like who collected the data sets as well. And that data collection is also accompanied by a user guide showing how to use the data sets. So for example, here in the case, how to eat the cookies itself, right? And then it also has metadata about variables and other as well. And in addition to the user guide, sometimes a data set can be also accompanied by details about the algorithms. For example, with the analogy of cookies, how to make a cookie, a recipe of the cookie can be an algorithm document, right? So algorithm document makes it possible to make that data set reproducible so that other people can also create similar data sets from where the data was originated from. So it has some of the required metadata such as spatial and temporal bounds, providing where and when, as well as additional attribute like how was it collected, what platform and instruments were used, and so forth. And the second type of metadata is the metadata about data granules, or those individual files that are within the data collections. So for in our example, the one cookie is one granule here, and so many cookies mean one data sets. So the granule level metadata can consist of information about formats of the individual granules, the links to download these granules from HTTPS. If the data is in the cloud, there would be a link to the S3 buckets as well, and spatial and temporal extent of the granules. So, and then what variables was measured in that particular granules as well as there are other information on platforms, instruments, and what missions collected that data set as well. So this is an example of data collection from NASA Earth Data website. So this particular data set is from NASA's Bioscape campaign, which collected data in 2024 from a range of airborne instrument over Cape region of South Africa. So these data sets provide information on surface thickness, this particular one from AVIRIS NG instrument, which is an airborne imaging spectrometer from NASA JPL. So if you go into this landing page here, we'll see several components of the data collection level metadata being displayed here. And in the right is the same metadata being displayed as a JSON file. So which is hard to read for us, but it's easier to read for computers, which can parse very easily and make out what the metadata, what that data collection is about. So if you want to explore more, here is a link that can open up that JSON files for you. So now this is the metadata about the granules. So if we go into that particular data sets, then it will list all the granules within that data set. So there are many thousands of those granules in this data sets. And on the right is the metadata about the granules. So this provides the links how to open that granules as well. But we'll go into details into this structure in a little bit. So the NASA Earth data uses a common metadata called CMR, which provides the backbone to all the metadata for the thousands of NASA Earth data collections and petabytes of granules. Now I think it's 5 or 6 petabytes. So the CMR shown here in the blue box in the center provides its own API and acts as a backend to Earth data search, so which is the core interface for discovering NASA Earth data. And the users can use Earth Data Search user interface or CMR's programmatic interface, such as Earth Access Python library, developed by the folks here at Openscapes. So some of the common options for the search may include the spatial, temporal, variable search, as shown in the green box here. And the search results, as shown in the yellow box here, can be about the data collections or about the granules. And also CMR uses metadata models, or called schema, to tie together all the metadata formats. So there are several schemas that NASA CMR supports, but two relevant here are one for the collection called UMMC and one for the granule called UMMG. And NASA also has developed its own control vocabulary called Global Change Master Directory, or GCMD, shown in the pink box here. So which provides science keywords, data formats, instruments in a hierarchical structure format. So this is the metadata schemas that provides a foundation for structuring metadata. So it also provides a predefined set of elements for describing the data. So as you can see, schemas provides the mapping for different CMR supported standards, such as ISO and older ECO format. So in addition to both UMMC and UMMG, there are also schemas on variables, services, tools, and visualization, etc. And this is the more information about GCMD you can find in this link here. So picture in the right shows the hierarchical structure of the keywords. And as we do our science, so we come up with new keywords and instruments all the time. And because GCMD is periodically reviewed, so we can add our new keywords and instruments and platforms to the GCMD periodically, so that it can be kept updated all the time. So this is an interface to the NASA Earth Data Search. So Earth Data Search is kind of a front end for CMR, so enabled by all the metadata that goes into the back end. And then it also enables capabilities for the search by keywords, search by platforms, projects, and space and time as well. So please go in this link here and familiarize yourself, because this is kind of like gateway to all the NASA data sets. So now coming back to the suborbital data set specifically, so this picture shows a range of suborbital or observation from airborne to field-based observation. I think I did this with the ChatGPT, and I think it did a good job of capturing variability of the suborbital observation data sets. So compared to those orbital data sets which are captured in the top here in the space, suborbital have a range of variability on the type of measurement they do and the platforms, and also what instruments are used to collect the suborbital data sets as well. And then so our task here is to ensure that these variability are captured well in the collection level and granular level metadata when we think about publishing these suborbital data sets. So suborbital data sets can be quirky because the same instrument can fly differently in a different platform at different altitude. So which creates different SWATs and grid size, for example, or same instrument may have a different set of calibrations for different campaigns. So the measurements might not be exactly same across the campaigns as well. And also so there might be additional variability because of the aircraft movement, and as well as local conditions like the weather might not be as suitable as well. So suborbital data sets usually needs a much more enhancement than standard orbital data sets because we want to capture all these variabilities, and we have come up with this concept of this enriched metadata for suborbital. So where all the details on platforms such as flying height, speed, and the details about campaigns and conditions of measurements, and also details about provenance of the data sets are captured in much detail as possible, both at data sets level and also at granular level. So let's look at this granular level metadata for one of the suborbital data sets into much detail. So this is the listing of the granules from average 5 facility instrument. So in the Earth data search. So if we click in one of the granules here and also click this view details in this block here, so it'll let us view the metadata. So you can go into this tab, metadata tab, and then if you click on UMG, it'll show what metadata this particular granule has. So now we'll go into a little bit of details on explaining each section of these UMG metadata so that we know what goes into each granule for just with the help of this one particular data set. So this is for the spatial and temporal extent. So this is one of the first things that needs to be provided for each granule. The spatial extent can be a bounding box or more accurately defined data bounds, such as polygons. So here is the screenshot in the right. So that describes a bounding box as a polygon and is showing the coordinates of like 4 vertices. So it can also be a lot more vertices as well if we were to define it more accurately as well. And the time extent can be a single date or with the beginning and the end period in universal time UTC format. And suborbital data sets can also be of varied formats. So some of the common formats can be like a CSV, a simple format, or GeoTIFFs, NetCDFs, SDF5, or iCard file, for example. And so most expectation is that these data files are cloud optimized where possible and also compliant to the data standards. For example, climate forecasting convention is the one that is used most for the NetCDF and SDF5 files. And platforms can also be listed as shown here in this right diagram here. So the platform and instrument has to be first registered as a GCMD keyword, and then it can be tagged as these in this format in the metadata itself. So one platform can have several instruments, which is usually a case. But in this case, there was one NASA ER2 platform, but it had only just one instrument, average 5. And then campaign and project keywords are also usually defined this way. So all the campaigns and project keywords also has to be defined in the GCMD keyword structure first, and then it can be tagged in as a granular level metadata as well. So one project can have multiple campaigns, so especially so for the facility collections like average, where the instrument has been being flown for many years now, and then each year it flies for different campaigns as funding comes through. So this particular files was flown for the GEMX campaign, which is now running on the Western United States to collect data for critical minerals and so forth. And there is also other attribute fields where a lot of other attributes that a data provider thinks is useful for the users can be put into. So this is not bound by any requirement by the UMMG format or CMR, but this is more free form kind of variables that can be thrown into here all the time. So some of the variables that we have seen that are put into these can be like software version that created this particular granule, or the name of the PIs, or any other information that can be that can provide more information about this suborbital data sets are useful. So this is I think my last slide. So all the effort that we do to make sure that metadata are done the right way, especially for the suborbital data sets, they all pays off when the data are published, because the metadata is what makes the data discoverable and accessible across platforms. So in the left here shows the Earth data search example on how data sets can be filtered using metadata tags. So here is an example with the UAV platform keyword to subselect the data sets. So on the right here are the several Python code snippets that shows how to quickly search the data sets and granules using various metadata tag that was used into that UMMG files when we created them. This can be like project or instruments and various ways to subset by space and also by time. They all use the Earth axis Python modules to create. So this all is possible because the right metadata is there for the granules. So hence the importance of the metadata that I want to point to. So some of these that we can keep in our mind, like when preparing data sets for the publications. So the more detail that we can provide in those data set level and granular level metadata, so our data sets would be in a good place for the humans and machines to find and being used. So now a lot of those concepts of AI-ready data sets are also coming into play. And then so these details about provenances and also platforms and instruments will be useful when we pursue that path in the future. Thank you.
Great, Rupesh. Thanks for
Thank you.
that great presentation.